I will be conducting a chemistry and careers project interview with faculty Matthew Bishop, and he is a marine geologist and also associate professor in the environmental science department at Fresno State. So we're going to start with four general questions. The first question being, what motivated you to specialize in alien oceanography and global geochemical cycles?
I had a research experience in Norway. So my last year of undergrad, while in France, I moved to Norway for 1 year. And then I had to do a research project, like one of the senior thesis. And one of the faculty over there was a paleoceanographer. And I liked his class. And I went to ask if he had any projects. And he asked me to he said yes. And then I could work on a project called that deals with what we call IRD, so ice rafted debris. When a glacier is flowing over the land, it is going to pick up a bunch of bits and pieces of rocks. And then all this is part of the ice. And when the glacier calves, when it makes an iceberg, then those icebergs are drifting with the currents. And eventually, as they go off the coast of Norway, they flow south, where it's a bit warmer, and they start to melt. And whatever content they have in the ice starts to then be released and then drops towards the seabed. And then we call those ice rafted debris. And the reason why those are important is because depending on where those glaciers were, in particular the Norway or Greenland, because the bedrock is a bit different, then if you study those bits and pieces, you know if those bits and pieces came from Greenland or if they came from Norway. And that tells you something about the currents that were in the North Atlantic at the time, and if they were more along the coast of Norway or along the coast of Greenland. So that's an indirect way to reconstruct the circulation in the North Atlantic by looking at what's happening on the seabed. I thought it was.
This question is going to be, did you have any experience that led you to earn your BS in geology?
What do you mean by experiences? Like, why did I go there? Or
so, like, experiences that led you to want to obtain that specific degree?
Oh, to get so I got that degree. So all throughout high school, I wanted to become a marine biologist. I was very much enamored with, all sea life, and that's what I wanted to study. So I went to Lyon University, and then I enrolled in the biology BS. And the first year we had a lot of biology. We had some plant biology, some animal biology, some microbiology, some plant population biology, all sorts. And then I realized that a lot of it was things that I needed to remember by heart, and then just regurgitated that on the exam, and it was just too much memorization for me. So at the end of the first year, we were asked to start to specialize in what we wanted to do. And I was, all right, plant biology, no. Animal biology, no. Microbiology, no. Biology, no. Population biology, no. And at the end, the only thing that was left was geology. And I then checked to go into geology. I always liked rocks, but not as much as biology. So I enrolled in that degree in a sense by default. And at the beginning of the second year, when I was fully in the geology background, I remember very well that the first class, one of the teachers said, if you are enrolled in this degree by default because you didn't know what to do, you will not do very well in this degree. And I thought he was actually talking to me. And it turned out to be good because there was a lot of field work, and I would always like to be outside. So it was it ended up being probably a better degree for me than biology, even though I still very much like biology. But I did not choose it because I was in love with rocks and minerals, for instance. I knew very little about them. I still know very little about them in the end. But it turned out to work for me.
Really interesting.
Mhm.
Not the norm.
Right. Yeah. I did not. I think a lot of my colleagues, we had discussed that in the department, have studied as geologists, I'm sorry, because they fell in love with the field, in high school or early on in their college degree. Well, me, it was again, it was a choice by default. It's because I thought that I could not do a proper biology degree and then be good enough with it. I just didn't want to commit the time to memorize everything that I had to memorize. So, but again, I think it was in the end a good choice. I very much enjoy it.
It's super interesting.
Mhm.
Like not the
Mhm. Mhm.
need to work back.
Mhm.
Another question,
Mhm.
what did you find most rewarding and most challenging about your career in environmental and earth sciences or geology?
As a student or as a faculty? So I think what I found the most rewarding as a student was the field work. I always like to be outside and then, doing a lot of looking at the outcrops, regardless of the weather, and then just being outside. I like that. I think what I thought was challenging was obviously the coursework. There was a lot to remember. And I think a lot of the students thought that geology was going to be easier than, let's say, biology. And I think because we are doing so much chemistry, so much physics, and some biology as well, in the end, it's a well-rounded degree, just like it is, for a mental scientist, for instance. But it's not an easy degree, right? It may appear from the outside to maybe being like a bit light compared to others, but I think that it's not the case, because there may not be the depth, but there is definitely the breadth as a student. And then as a faculty, what I find rewarding is I think the teaching. I enjoy um, being in the classroom, and then regardless of what the class is or what the material is, I enjoy that. And what I find challenging is obviously sometimes I'm not able to convey well enough why something is important or why students should be paying attention. And I sit in all the classes, including this one. For instance, like I'm teaching Python to the class, and I think that I can tell that some students would rather do anything but that. But what I'm trying to convey, and maybe not well enough, is that this is a nice skills, a tool to have under our belt, because it can really expand what we can do in terms of research. And I think that's going to become a bit more clearer in the weeks to come, where you'll be asked, to incorporate more and more data. And then if you were to do it in Excel, for instance, I think it would take a lot more time. So I think Python has that possibility to be able to do that. But that's the challenge sometimes, is to be able to. We're not computer scientists, to begin with, and I think a lot of us would rather do anything but a bunch of coding in front of on a laptop. But it's not so much the coding that is important as much as what we can do with it. And I think this is what we'll try to expand on over the next few weeks. So. Mm-hmm.
During your as a professor,
Mm-hmm.
how do you feel it's been challenging, like with the different like technological advancements in conducting field studies?
So I think that's going to be one of the questions that you'll have for me next, about for instance, the LiDAR and the UAV, right? So this is a couple of new toys that we have in the department, and I was not trained with any of that. Like you said, I was trained as a marine geologist. My field is more the ocean. And I've never been a video gamer, so I'm not, necessarily very good with a remote control. I never had drones growing up, or until just, we bought one. So I think this has been a challenge because it's a bunch of new techniques that we have to learn. And right now in the department, I think I'm the only one that's really, took a keen interest in all this. But it's at the same time very fun because it keeps you on your toes, so to speak. It allows you to do something a bit different, and I think I like those challenges. I think intellectually it is interesting, and I see the value because I understand what it will allow me and therefore the students to do in terms, of research projects in the future. So, and it's the same with Python. I didn't know anything about Python until a couple of years ago, to be honest with you. Well, maybe about 3 years now. But, and at first it was like all difficult and foreign, but I understood what it could do for me. And when you understand what a technique can do for you, when you see the use for it, then you're more willing to spend the time to learn about it, even if there is, a steep learning curve in the beginning. If you have to learn something just because you have to learn it for class, it, it becomes quite a bit more difficult because you're not interested in it. And if you're not interested, then you're not willing to spend the time learning about it. You're not open to what it could do for you. But I'm not with the new technology that I'm trying to implement in the class and the research. I do it because I want to. There is nobody that forces me to do it. And I do it because I see, again, a value to what it can allow me to do in terms of, expanding the research. So it's a lot easier. Mhm.
Mm-hmm. As an educator and a researcher, how do you balance teaching courses like ES 109 and conducting fieldwork, such as your studies, like as in Morro Bay in Sandsville?
Right. So I think what would be easier if I could, use 109 to conduct research. If I were an atmospheric scientist, for instance, I could use the class to also collect data, for instance. The reason why I'm teaching 109 is because in the department, I'm the most qualified based on coursework and interest to do a class on climatology. Again, when you are a paleoceanographer or paleoclimatologist, I've had to take, classes in on the weather, for instance, or the climate. But I did it again because it was useful for my research in marine geology at the time. And when the class was placed in the catalog, I think a few years back, I think Beth started to teach it first, and then eventually she just gave me that hot potato, and I've been teaching the class ever since. I have an interest in the climate very much so, but I'm not an atmospheric scientist. Okay, so I cannot combine the two. So to do what I do for research, for instance, in terms of coastal geology and 109, there's no real overlap between the two. But where I'm lucky is that I'm allowed to put a bit more, one or two more classes in the fall, so that my spring is a bit easier. I only teach 2 classes in the spring, so that frees quite a bit of time to do other things, such as conducting more research in Morro Bay, for instance. So there's no overlap, but I have enough time in the spring that I can do both. Right. Mm-hmm. Yeah. Mm-hmm.
So now we're going to transition to more science questions. The first question is going to be, so based on my research, your coastal geology research utilizes LiDAR mounting on UAVs for high resolution imagery. Can you elaborate on how this technology has advanced your analysis of coastal erosion?
Sure. So a LiDAR is a fancy word for light detection and range, and it's a laser scanner. Okay, it looks about that size, and there is a head that spins, and then that sends a bunch of lasers in 360 degrees. And we have it mounted on a large drone. large enough that it's, I think, payload capacity is, I think, like 20 pounds or something like this. So it's beefy enough that we can lift the drone, the LiDAR, I'm sorry. And the reason why we are using this is because back in the days, if you wanted to look at how the beach changes over time between, for instance, so during the winter, the waves are a bit bigger, so they tend to erode the beach quite a bit more, and then that same shoreline rebuilds in the summer. And we want to know how much is being removed and how much comes back during the summer. And back in the days, we would do that by starting maybe from where the sea is and then walking towards the beach. And then every few feet, we would use a stake, and then we would calculate how high it is compared to a reference point. That works out well, but it only gives you a few points along what we call a transect from the beach to the sea or vice versa. And if you wanted to, if you have something that is very long, a few miles in length, for instance, then you would have to do hundreds of those transects one at a time, and that is time consuming. And again, in between two transects, you can have maybe 100 feet or 300 feet or more, then you don't have any data. So that means that you need to interpolate the data. You need to think, if this is high, this is low, then somewhere in the middle, then, it's going to be average, okay? But with the LiDAR, then we can scan everything. And we don't have to walk. All we can do is just take off, and then the drone can do everything automatically. And per square meter, we have hundreds of points, meaning that we know, all right, so if this is the ground right here, then right here we have a bump, and then we know the position of that bump, and we know exactly how high it is compared to a reference point. And so it gives you a lot more data and a lot more precise data. And because you in one day you can scan, so the Morrow SensePit, for instance, is about 8 miles in length, and in one day you can scan all of it. If you had to do it with transects, it would probably take you, I don't know, if I had to guess, maybe like a week. And the advantage of doing the LiDAR, therefore, is that you can do a lot more studies. If I only need one day to do one study, then I could do maybe, once a month, for instance. And then over the course of 1 year, I have 12 maps. Well, if I would need 1 week, I cannot take off work, 1 week every month, for instance. I have other things to do. So I could only do it maybe during the winter break and the summer break. So now I would only have, maybe 3, 4 of those studies. So a lot less and not with the same quality. So this is allowing anybody to have a lot more data and a lot more accurate as well.
So the technology is attached to the drone?
Right. Yeah.
You said the stakes
Mm-hmm.
in, I believe, like we did that with San Joaquin, Chinook, San Maria. Okay.
Right.
So
Right.
you could same technology.
Right, you use that same technique, the Jacob staff. And then if you did it with, did you measure like the profile of the river? But you saw that it takes a long time. Plus you were in the river, you have to walk across. So if you're on sand, it's a lot easier. You don't have to worry about the water. But you also, you only did it, a few feet, every few feet. So you can imagine that again, if you have a bump, in your river that you don't see, and then you can miss it, and then you don't have the data in between. So what you're going to assume is that if again everything's at at the same height, that again in between everything's at the same height, when really there could have been like some a change maybe, or trough, right? And that's just the way we did it back in the days. That's how we continue to teach all of you how to do it, because we want all of you to know how it's being done, because not everybody has access to that technology, and sometimes it's the way to do it. But they are now much better techniques if you have access to the techniques. If you don't have access to the techniques, then you you're out of luck. And we're lucky in the department that we have access to that drone and that LiDAR. The problem is that LiDAR emits a wavelength that does not go through the water. So we could not do what we did on the beach, to scan the river profile, for instance. It does not penetrate through the water, unfortunately.
Surface.
Right, right.
Misunderstood.
No, so it passes through, if you have a forest, for instance, there's enough laser energy that passes through the canopy to go all the way to the ground, so you can see what the ground is and the shape of the ground. But water, that's not the right wavelength. We would need a longer wavelength that could then penetrate deeper into the water. And those LiDAR scanners are quite expensive.
Phone apps.
Yes, but on the phone, the one that you have is just like what we have on the drone. It does not allow you to go into the water either. You could, scan, somebody, and then it's the same ID. It sends, a bunch of lasers, absolutely. But it does not penetrate through the water. It's not the right wavelength for that. Mm-hmm.
Is what challenges do you face when integrating data from various sources, such as sediment cores and geochemical analysis, to understand historical climate patterns? This is redirecting towards your.
Mm-hmm. So one of the main challenges is so the way I did it for the PhD and then a little bit here is you request samples that come from a sediment core, and sediment core is really about that wide, and then we again drill through the seabed and then we collect sediment or rocks that way. And the problem is sometimes it's the only one that we have for a very large area, and we are going to then find, I don't know, what was the temperature of the ocean or what was the productivity of the ocean right above that area. But if we want to extend those results to a much larger part of the ocean, then we have to make some assumptions. And one of the assumptions that we have to make is that, the ocean 100 miles away behaved in very much the same way as around here, meaning that if it were warm here, then it was warm over there as well. And that assumption is not sometimes correct. It's the same as, finding what's the temperature in Fresno. And then from this, trying to deduct what is the temperature in Sacramento. If it is warm in Fresno, it is likely to be warm in Sacramento. But because it's further north, it's going to be, probably a bit cooler by a few degrees. But at the same time, if you have a bunch of rain that passes over Sacramento, but not Fresno, the temperature in Fresno that you register is going to be now quite a bit different than what it is in Sacramento. Okay, so the problem that we have is we have one data for one core in one place, and and that's not necessarily correct, we like to try to generalize that to a very much larger area. And the reason why we do that is because we don't necessarily have data anywhere else. It's like, again, going back to the analogy of the temperature in Fresno and Sacramento, if we didn't have any weather stations in Sacramento, but we wanted to figure out what the temperature was, we would be forced to use what we have in Fresno. And most times we'd probably be correct, but at other times we wouldn't be. And so unless we go out in the ocean and start to have cores everywhere, we are forced to make those generalizations. And what has been shown time and time again is that, sometimes we make those generalizations and then we go into that area, we pick a core, we analyze it, and then we realize that it is not the same whatsoever as what a study in the past had said, because now we are more detailed. Just like that'll be the same as, again, for 50 years, you use Fresno to deduct the temperature in Sacramento, and now you start to place a weather station in Sacramento, and you realize that the weather is not the same as what it is in Fresno. Quite often it's, on par, but quite often it's also quite a bit different. And that's because you have more data. Mhm. Mhm. Samples. Mhm.
It's the core samples that they show ES 114.
Mhm.
Samples they
Right. So these are made of rocks, and then you have the same made of sediments. So if you have rocks, then you know they're going to cut a small piece of the rock and then send it to you, and you can do like I don't know thin sections, for instance. I don't deal so much with rocks, only with the sediments. And then when you have the sediment, then they just cut it in half, split it in half, and then they have tiny plugs, and it just push a plug into the sediment, twist it, and then bag it, and then send it to you. And then you right, yes. And then you have a few grams of sediments, and then with that, then you do whatever study you have to do. So what I studied for the master's and the PhD are tiny marine protists called foraminifera. They have about the size of a grain of sand, and they are animals, if you want, that make a shell made of calcium carbonate. Um, um, for protection. And depending on the species, then the shell is going to have different shapes. And some of the species like warm water, some like cold water, some like no oxygen, some like a lot of oxygen. So depending on how the ocean changes, if it becomes warm or cool, for instance, then if it's warm, then you're going to have a lot of warm species. And then when they die, they settle through the water column and then they get buried. And then you start to record a bunch of warm species. And then if the ocean above becomes cold, then those warm species migrate somewhere else and they're being replaced by colder species. And then those colder species will eventually die, settle through the water column, get buried into the sediment. So now you have a bunch of warm species, cold species, warm species, cold species. And then you can track the change in temperature of the ocean through time. Mm-hmm.
They said there was another question.
That's okay.
Questions in space that I had was how do yeah, we didn't talk about this. How do physical oceanographic processes such as wave dynamics and sediment transport influence coastal erosion and deposition?
So you can imagine that when it is the winter in California, we have a lot more storms, right? Let me rephrase that. So for us on land in Fresno, during the winter, we have quite a bit of rain compared to the summer, right? Summers tend to be generally very, very dry. And if we have a lot more rain, is because then out in the Pacific, there are storms that are bringing that rain towards us. And if you have a storm, then that also generates a lot of waves. And so the waves in the winter in California tend to be taller. And if they are taller, then when they crash on the shoreline, then you can imagine that they are bringing more energy and it's easier for them to remove the sand. And then when a wave crashes, then it recedes and then brings some sand with it. And then that sand is going to then be accumulating into a sand dune, but that is offshore, so underwater. So that's why we don't see them. And then during the summer, when the waves are a lot smaller because we don't have those storms in the Pacific, then slowly but surely they are able to push that sand back onto the beach. So during the winter, it erodes. It becomes usually, um, smaller and then thinner, the amount of sand, while during the summer, it aggrades, as we call it. So it rebuilds. So that's how, again, those physical characteristics are going to influence the shape of the shore. And what we're trying to figure out is, well, if you have waves that are, I don't know, 10 feet high, for instance, how much sand is really being removed compared to, let's say, 15 or 20, okay? So it's one thing to say, oh, sand is being removed, but what we want to do eventually is figure out how much sand is being removed. And that's where the LiDAR comes into the picture because it allows us to make a nice map. And then, so you do a map, on January 1st, you do a map on January 31st, a month later, and then you compare and contrast the two maps. And then we do that with GIS. And then, you know, if this is the map, the first map where the slope was like this, and then the second map is like that, then you know that everything right here is now missing. So that's how much you can has been eroded, for instance.
Yeah, so you're showing like slope and then you're doing, are you also showing
Right. So you create a bunch of slopes. Yeah, it's the idea that so it's a bunch of slopes, right? And then in the end, you end up if you know if this is so the ocean is right here and this is you know the beach right here, for instance, then you know you have a bunch of slopes right there, and then so that's on January 1st, and then you come back in January 31st, and everything is like this now. So if you compare contrast, then what is in between the two profiles is again what has been removed, and then in GIS, and again I don't know how the program you know itself works, but you can estimate you know how much is in between the two profiles, and that's how much sand has been removed. And then in the summer it'll be the opposite. You start you're pretty steep like this in the at the end of the winter, and at the end of the summer then you're back to a more you know normal profile. And what is in between the two right here is how much sand has been added onto the beach.
there's like a transfer?
Right. Yes. So there is a transfer of sand during the seasons, and the goal is to want to quantify the transfer. Is it, I don't know, I'm just going to throw a bunch of numbers, you know, is it 1,000 cubic yards of sand or is it 500, for instance? Okay. And the goal after that is to try to relate that to the storm activity. So if you have uh, a bunch of large storms and you can quantify, you know, how much those storms, how big they are, then the goal is to try to then quantify, oh, if we have those kind of storms, then we're going to remove 1,000 cubic yards of sand. If we have those storms, it's only going to be, you know, half of that. I'm sorry? So the LiDAR technology will allow you to figure out how much sand is being removed. And then for the storm activity, then NOAA, so the National Oceanographic and Atmospheric Administration, has a bunch of buoys out offshore. And what those buoys are recording is, for instance, the wind speed, the wind direction, and the wave amplitude. So how big are those waves? And using that information, then we can, there are equations that are indexes that allow us to say, like, all right, if you have this, this, and this, and this, then that's going to be a, I don't know, a category 4 storm, for instance, or category 1 or category 2, whatever it is. And the goal is to figure out, all right, if you have a category 1, then you remove 50 cubic yards. If it's a category 2, then maybe it's 100 cubic yards. If it's a category 3, then now it's, you know, 150, so forth and so on. So the goal is to try to create, you know, a curve where you would have storm on one axis, storm strength on one axis. You would have how much sand is being removed, and then the goal is to see, you know, what kind of relationship you have. Is it a linear relationship, for instance? Yeah, you know, is it an exponential decrease like we talked about before? You know, um, for pressure, for instance. So again, the idea is to try to be able to predict. All right, next week we're going to have a category 5 storm, so we know we're going to remove, you know, X amount of sand, for instance. Good.
Kind of,
That's okay. That's all right.
I'm interested in various aspects of the different research.
That's okay.
Hard to focus
Of
on.
course.
But now we're gonna redirect the questions
Mhm.
towards chemistry
Mhm.
and how chemistry played a big role in your career,
Mhm.
per se. So I will start with the first question. This is a more general, like simpler question. I
Mhm.
think. How do variations in ocean chemistry, such as pH or salinity, influence the preservation of the geological records in the marine sediments?
So maybe you remember in your ES1, do you take ES1? No? Okay. So in ES1, one of the labs that we have the students do is take a piece of calcium carbonate, limestone, and then we put a little bit of acid on it. And when you put acid on calcium carbonate, then it fizzes, it dissolves, okay? And then we can then relate that to pH. So the idea is that when the ocean becomes acidic, then your organisms that form a shell made of calcium carbonate have a harder time either making the shelf or continuing to make the shelf. So a good example of that are corals, for instance. Corals only cover about 2% of the seafloor, but they harbor about 25% of all living species in the ocean. So a tiny footprint on the seafloor, but again, a quarter of all species in the ocean live in and around corals. And a coral reef is made of marine organisms called polyps. They usually have the size of your fingernail, your pinky, if not smaller than that. There are a bunch of tentacles as well. And for protection and support, they're going to make a what we call an exoskeleton around themselves. Okay, and that exoskeleton is going to be made of calcium carbonate. And when the ocean becomes more acidic, then that exoskeleton starts to dissolve, or it becomes a bit brittle. And if it becomes a bit brittle or it dissolves, then when you have waves pounding onto the coral reefs, then those coral reefs start to break apart a lot more easily. And if they break apart more easily, then the polyps themselves are not protected anymore. So either they go somewhere else or they die. And if they are going somewhere else or dying, then all the species that live in and around the coral reefs, now they have to go somewhere else as well. So pH is important because so right now the ocean is about basic, it's about 8.3 in pH. But if it becomes a bit more acidic, and it's on its way to right now, then it's a bit harder for some corals to thrive. When for the small guys that I study, the foraminifera, if it's too acidic, same thing, the shell dissolves, or it becomes a lot harder for the animal to make a shell around itself. So that's the impact. So if it becomes too acidic, then the limestones start to disappear, and then we are losing that record from Earth history. Salinity, if it's too salty, then a lot of your organisms are not going to like that. If it becomes too fresh, they're not going to like that either. They have evolved over time to be in a certain range of salinity. But if you have, let's say, a large glacier that melts and that releases a lot of water all at once, and the water becomes a lot fresher all of a sudden, then a lot of your organisms may have to go somewhere else. But if they cannot, then they're going to die, and that's the end of it for them. If your ocean becomes too salty, then again, your organisms eventually cannot deal with too much salt, and either they go somewhere else or they die. And that's, for instance, what happened in the Mediterranean Sea about 3.7, 3.8 million years ago, where it almost completely dried up. And what we can see is that a lot of the organisms died, A, because there was no water, but even before that, because it was simply too salty. So chemistry is very important for marine organisms. It's important for you and I, and it's definitely important for a lot of them, for all of them as well. Mm-hmm.
About larvae.
Mm-hmm.
I believe so, 167.
Okay.
Versus putting them in different fish tanks
Mm-hmm.
and comparing like to see how they would survive and whatnot. And then it talked about their cytoskeleton,
Right.
calcium carbonate protection.
Mhm.
So
Right. Right. So this
Yeah.
is a type of experiment that you could do where you are, acidifying the water, and we do that usually by putting CO2 in it, and then so if you put CO2 from the atmosphere into the ocean, that changes the chemistry of the water. CO2 is going to combine with water molecule to form an acid. H2CO3, if I remember well, and then H2CO3 then dissociates into HCO3 and then one H plus, and H plus is how we measure acidity in the water. If you remember, maybe pH is equal to negative log 10 of the concentration of H plus. So the more CO2 in the atmosphere, eventually the more CO2 in the ocean by diffusion, and then from there we start to acidify the water, the seawater. But like I said, it starts at, seawater is around 8.3, so it's basic in terms of pH. And right now it's going to about 8.1. So when we say that we acidify the ocean, it will never become acidic. It will become less basic. But because everything is on a log scale, when we're going from 8.3 to 8.1 in terms of the pH, really it's an increase of about, if I remember well, I think like 30% in acidity, which is huge for some of the species, right? If something becomes 30% more acidic, it's
dying.
right, and that's what a lot of species, are not faring too well. But what we also seeing is that some corals in particular are able to adapt to this. So there's a lot that we still don't know about how the ocean and the organisms in the ocean will react to acidity. On paper, it looks like it's not going to be so well, but we are seeing that there is maybe a bit more resilience for some species. Not all of them, clearly, but some species are more resilient than we thought they would be. Right, right.
Do stable isotopes like
Mhm.
carbon-13 and oxygen-18 help reconstruct past ocean conditions, and what lab techniques are commonly used for these analyses?
So the lab technique that's used is what we call mass spectrometry. So a mass spectrometer is a piece of equipment where there's a large magnet, and then the oxygen or the carbon are passing through the magnet, and depending on their mass, they are deflected more or less. And what I mean by this is, so we have oxygen 18, 17, and 16. The two most important really are 18 and 16. And out of those two, 16 is the most important. So when we form water, H2O, we form water with H2 and then 18O, some 17O, and then some 16O. Okay. And when that water evaporates, then the 16, so the water molecule made of 16 oxygen, because it's a bit lighter, evaporates more easily than a water molecule made of oxygen 18. That's what we call diffraction. And so your cloud is going to be enriched compared to the water. It's going to be enriched in 16 compared to 18. Okay. And as the cloud is going across the ocean and then onto the land, and then water starts to form or snow, then the water that comes out of the cloud is going to be more, and it's going to be enriched in 18 compared to 16, meaning that the raindrops are not going to have the same ratio of 18 over 16 than the cloud. Do you follow me?
Try.
Oh, I can turn mine. Oh, I don't have, oh, I need to remove background then. Can I remove the background? Because otherwise, just background, remove the background. How do I remove my background? Yeah, we might have to. Oh, what if no? Oh, no. Okay. All right. Okay. All right. So is that going to? Yeah, you'll be able to. All right. So you have in the water, you have a certain ratio of 16/18. Okay. When water evaporates, then this class right here is going to have, it's going to be enriched in 16/18. And that's because, again, the 18 is, it's a bit easier for it to evaporate, okay? And then when that moves onto the land, and then we start to have water right here, the water is going to have more 18 and 16. Okay, and that's because this is a bit heavier, so it's easier for it to precipitate. Okay, and so what that means is that over time, the concentration of 16 into the cloud becomes bigger and bigger. Okay, and then when you go further out, then there is more and more, the water in turns becomes more and more enriched in 16. Okay. Okay, the reason I say that is because how much 16 evaporates and finds itself right here depends on temperature. And how much 18 rains down compared to 16 also depends on the temperature when the rain forms. Okay, so what that means is that we can use that ratio as what we call a proxy for temperature. Either the temperature when it evaporated or the temperature when it precipitated. Okay, and a proxy is an indirect measurement. And what I mean by that is, so we can do it today, right? But if we go back in the past, then all we have is, for instance, the that ratio into a shell, where we call it test, something. So we can use the ratio inside that test to figure out what was the ratio in the ocean, and that is also temperature dependent. So what it means that how much is in the test, in the shell, depends on the temperature of the ocean when that organism formed the shell. And we have equations that then relate temperature to that ratio. And what that means that if you know the ratio, then you can infer what the temperature was. And that's huge because it means that we can now, if this is the ocean, and then right here you have a cone, and then inside the cone you collect a bunch of those, you analyze those, and then you have now a depth, and then right here's your ratio, and then you have a bunch of wiggles. Then depending on how these vary with depth, then you can reconstruct what the temperature was at the time that those shells were forming. But it's an indirect measurement. We don't have a thermometer during that time, but we can use that ratio to do so.
This is like more than chemistry, it's like everything.
Yes, it's a lot. You're right. So it's not just
Wow.
yes, it's a lot together. You're right. But it at the base, it is a lot of chemistry, but it's again chemistry applied to the study of the environment. And I think this is where, it becomes, I think, very, very neat, because I don't think I could have become, because I don't know enough, but I don't think that I could have become, a chemist for the sake of being a chemist. But now, using chemistry when it is applied to the environment and the climatology, now that becomes interesting. It becomes a tool that is very valuable. So that's what we can do with oxygen 1816. For carbon 13 and 12, your organisms, they would rather feed on 12 than 13. And what is happening is that when there is plenty of carbon 12 in the environment, that's the one they're going to choose to form their shell, for instance. But when and eventually if they have to, then they'll go to 13 nonetheless. So a change in the ratio usually is going to be indicative of the biological productivity of the ocean. So we can use it as a way to reconstruct the amount of nutrients that used to be in the ocean, for instance. Okay. I'm a bit less familiar with this because I did not have to use it too much. I did a bit more of that in the in grad school. But we are using them to again reconstruct a change in the environment back in the days. Mm-hmm. Of course. Mm-hmm.
Already, but it was about your research involving the marine calcium carbonate budgets.
Mm-hmm.
So what chemical techniques do you use to measure and analyze these variations in chemical cores?
So right, we did a little bit of that, and then yes, so you can definitely do some of this, and then I did also some a bit more advanced geochemistry that was using some radioactive elements, and without going into too many of the details, but the idea with this was to be able to reconstruct exactly how much of those organisms were accumulating on the seabed. And the reason I say that is because we have currents on the seabed that can bring sediments from outside the area, what we call focusing. So we are focusing sediment into the area. And if you have a bunch of those sediments, what we have said in the past is that if you have a bunch of sediments, then you must have had a lot of organisms from above that were thriving, when really it is possible to bring that sediment from the outside. And if you bring it from the outside, then you are overestimating how much is really coming from the top, directly from above. And with those other geochemical studies, then you can try to tease out how much is coming straight from above versus how much is coming from the side, so that you can really reconstruct just what is coming from above. So the analogy for this is, imagine that you have a bunch of food on the table, and we see you next to the table, next to a cook stove. We could imagine that you made all that food, right? Or we could say, well, we know that you made, the pasta dish, for instance, and the something else, and then the rest of the food was brought by other people. And what we want to know is how much you made of the food. And the only way to do that would be able to find a method that allows us to say, all right, this and this you did, but the rest I brought it, Mara brought it, Eric brought it, or Alicia, or whoever else. Okay. So the idea is that if you imagine the table as being what you reconstruct coming from one place in the core, then we want to be able to tease out, okay, so much of that food, so much of that sediment has been brought by other processes because we have currents on the seabed that flow in, and how much have you actually made? And the reason for that is because if you made a lot of the food, if you made all of the food, then what we can say is that you had a lot of ingredients, right, to make all the food. But if you only made colored dishes and we see a lot of food, then what we can say is like you didn't have all of the ingredients to make all of the food. You only had access to, you know, a lot less ingredients, and those ingredients would be the nutrients.
When you say, so is that when that transfer comes in again? Does that apply like the transfer from like the waves?
No, so
This is the
that's much deeper,
extraction.
right? That's much
Okay,
deeper in the
okay.
ocean, but they are currents. So there is moving. We shouldn't be thinking that the ocean is just moving at the surface where we see the waves. Underneath the surface, there are also very large currents. We don't see them, but we can measure them, and they can move sediments around quite a bit as well.
Going back to this topic,
Mhm.
you discussed the role of stable and radioisotope studies in your research and how they contribute to the understanding of oceanographic conditions.
Right. So I don't do it directly anymore because we don't have the equipment on campus to do that. But I did some of that in grad school. So you can do, again, oxygen 18 and carbon 13 to reconstruct either the temperature effect, or I'm sorry, the temperature on the nutrient availability in the ocean. And then the radioisotopes, it's what allow me to distinguish between what came just from above compared to what was brought from the side in the same place.
Do you feel like you focus more on carbon?
I could have, but the reason why I did not, I mean, sorry, let me rephrase that. Do you want me to explain more of this, or do you want me to explain why I did not focus on that during the PhD?
Can you explain it? The carbon.
So the so the ratio 13/12 is usually used as a ratio for or a proxy. So again, indirect measurements for nutrient availability. If you have a lot of nutrients, you're going to have a lot of 12, and your organisms that feed on those nutrients, they'll tend to use the carbon 12 before they do the 13. Okay, so what I mean is that their composition is going to be rich in 12 and poor in 13. Okay, but when the amount of nutrients decreases and all that's left behind is the 13, those organisms have to eat nonetheless, and they're going to start to eat the 13 by default. And what it means that themselves are going to be made of a lot more 13 than 12. And when we analyze two organisms, one with a bunch of 12 and one with a bunch of 13, the way we interpret this is by saying that the one that's made of 12 formed at a time when there was a lot of nutrients and it could be choosy, while the other one that has a lot of 13 formed at a time when there were not that many nutrients, and beggars are not choosers, so he had to use the carbon 13.
Is there a way? What?
Does that make sense?
Yeah. Is there a way that, because it's you guys are focusing like on past like,
Mhm.
ocean conditions,
Mm-hmm.
how do you know that it was past conditions? Like, are you able to differentiate like
Oh, because for instance, you can date you can date the sediments.
So this is the cores. But
Right.
How do you know which cores are older than others?
So which
Like,
layers?
by an animal.
So just like if you have a layered cake, right? If you have a cake made of different layers, the layer that is at the bottom of the cake is the first one that was placed on the counter, right? And then you built up from there. You were not able to somehow have the top layer levitate, and then you built it from the top down, if you know what I mean. So same thing when you have layers in the coal,
Right, 'cause it wouldn't be
right?
the same
Like a
height.
solar horizon, yes. The layers that are at the bottom are older than the layers on top. So when we are coring the seabed, we know and we collect, I don't know, like usually it's about 5 feet in length. Then we know which part is the top, which part is the bottom, so that we don't flip it around, otherwise we miss everything. And then when we are splitting it into smaller samples, we know, that one came from the surface, that one came 2 inches from the surface, 4 inches from the surface, so forth and so on. And if you came 2 inches from the surface as opposed to the surface, then it's older in time.
This question's kind of
That's
like
okay.
answered each subsection for the question.
Mhm.
Is there anything that you would like to share about chemistry in your career, or any general questions on regards to science?
Right. Something that I would like to share is something that I don't think we see enough in undergrad, unless a student decides to do a senior thesis, for instance, on let's say geochemistry. The chemistry that you learn in Chem 1A, Chem 1B is or more is always very useful and interesting, but it's never as interesting as if it could be taught by one of us, by somebody that does earth elemental sciences, because then the examples would be only drawn from their experience. Learning about pH is neat, but when you see how it can be applied to life in the ocean, for instance, then I think that makes it more relevant. And because it's more relevant, then I think it is easier to grasp the concepts and to be willing to learn about it, because it's, again, applicable. And it was the same for my undergrad, the way it's being taught, it's taught by chemists, and they have other reasons why they would want you to learn pH. We do applied biology, applied math, applied physics, applied chemistry. And you took Calc 1, for instance, and I'm sure that it was not necessarily that relevant to you at the time, but you've seen in this class that we apply calculus to, again, understand why, again, how do we know that pressure decreases exponentially with height? We use calculus for that. Things starting to make a lot more sense for me, what I've learned in chemistry, biology, math, and physics, when I really started to apply it to the field of earth elemental sciences. Before that, it was never as relevant and therefore interesting and valuable to me. Again, I go back to the idea of, if something is valuable to you, if you see the value in it, then you'll be willing to spend time learning about it and go deeper into the material. If you don't see the value, then it's just something else that you learn for taking an exam, but you're not going to retain it for anything else. So I think what I've learned over the years is that if I see the value in it, I'm willing to learn a lot more about it, and I'm willing to and I'm going to understand it better. And unfortunately, I think in a undergrad degree, a lot of what you're learning is not applied enough that it makes sense, unless you start to do an internship or a senior thesis, and then as you go maybe into a master's, for instance, then you'll start to see, oh, okay, that's why I had to learn what, the equation for pH, for instance. So this is why I like to learn, that's why I had to learn how to balance an equation. Balancing an equation, if it's just done like that, what's the point? But if you now do it because you try to, get rid of pollution in a soil, for instance, now you understand why you need to balance your equations. Because if you don't, then it does not work.
If it was more like applied, like on, or more applied to like daily, like life, or whatever interest that you had,
Mhm.
people would have a better understanding and
Right.
be able to,
Right, and that's what, yes, I'm convinced of that. Again, right now we've been learning about Python, and yes, you know how to graph. Great. What is the point of that? But you will see that if you're doing a senior thesis and you have to deal with a bunch of data where it becomes too much for Excel to manage, for instance, then now you'll be like, okay, now you understand why, a simple line of equation allows you to read a very large file, and how from a line of equation allows you to calculate a monthly average, for instance, without you having to click and drag all over the place. So unless everything is, either part of a project that you're interested in, again, it becomes something that at the end of the semester you forget. And it's not you, I forgot, many things that I've learned as well over the years, because it was like, all right, what's the point? I'm never going to use this. And too many times do I hear students like, oh, why do I need to learn this in chemistry? And unfortunately, it's because and again, that's not the fault of those chemistry teachers. They have so many things to do as well. But the way they taught it, they teach it, is not related to our field. Because, you have biologists that take chemistry. You have biochemists that take it. You have people that take it just because they want to go into nursing or med school later on. So they took it for that requirement. But if you were to take geochem, for instance, or biogeochem with Eric, for instance, now you start to see how the chemistry is applied to, again, what we see around us, what is of interest to us, which is the environment.
Can I test on that?
Mhm.
Do you see that? Taking the more general courses like chemistry, like introduction
Mhm.
courses, taken less seriously in comparison to my upper division. I've taken geochemistry, I've
Mhm.
taken so I'm in 150T,
Mhm.
and it's more applied,
Mhm.
and so like a different approach
Right. Mhm.
in
Right, because now you see that if you want to understand the material, then you also need to understand the chemistry that is underneath, that underpins, all of all the processes. And you need to, yes, and you'll have to go back to the basics. But and that's just the way it is. I did quite a bit of math just for fun. I went all the way to Calc 3, and that's only when I was able to relate it to some of the classes that I have taken in geophysics, for instance, on the weather modeling, that I was like, oh, that's why we're doing this and that. But before, it was just, again, taught by a mathematician that did not necessarily thought of the applications, was not necessarily interested by the applications. They'd give us, a bunch of examples for because they, in a sense, they have to. But sometimes I feel that if they could just go with the theory and not the applications, they'll be just as content. I think a lot of those teachers are, pure chemistry or pure physics or pure mathematics, and for them the applications are not as interesting as the pure aspect of it, and that's just what they like. I'm more of a applied scientist than I am a pure scientist in that sense. Mhm. Right. Right.
They all
Exactly.
interact with each
Mhm.
other.
Yeah, I agree.
sharing.
You're welcome.